All right, folks, it's Bass Action back in action here. In this video, what we're going to look at is just an overview of systems of three variables. Now, you've seen this in your Algebra 2 courses, but we're going to combine these ideas with systems later that are nonlinear systems. So the things we're going to cover here are important in terms of the skill set, but on this page, we're specifically going to understand solutions and some vocabulary for our linear systems in three variables. So up here at the top, we need to first understand that an equation in three variables, all to the first power, that first power is important to us here, is a plane. Okay, now you remember from your geometry days that planes are named with three letters. And then in your geometry days, you also looked at the intersections of planes. So the intersection of three planes has three possibilities. They could be a unique point, okay? And if you're trying to visualize that, you can certainly go look at your textbook that has some good images of that. But you can also look around in the room you're in and look in the corner of the room where two walls and the ceiling intersect, and you have the nice corner there that's your point. We also could have a line, so think about the wall and the ceiling and the crease that's up there at the top, or it's possible that they have no intersection at all. Think of 3 floors in a building. The first, second, and third floors certainly don't intersect at all. There is one other scenario where we could consider a no solution, and your textbook has a good image of that. But for our purposes, just think it's possible that they don't intersect or have anything in common. All right, so our systems with one solution, okay, would occur when, exactly what I've set up above, when they only have 1 point in common, okay. That solution is said to be consistent, okay. Sometimes this vocabulary gets difficult for students. Consistent and independent. Depending on your teacher and how much they use that vocabulary, you might need to be more familiar than others. The solution is written as x, y, z. Now, certainly your variables might not be x, y, z. We just put them in alphabetical order, and it's called an ordered triple. Just like we have ordered pairs, since we have 3, we have an ordered triple. Then we're going to have our infinite solutions, okay? So when we have our two planes intersect and there's an infinite number of points in common, okay, so this is an infinite points. Okay, so our infinite solutions would mean they have an infinite number of points in common. That solution is said to be consistent also. Consistent, think of that as meaning there is a solution, okay? Consistent but dependent. And then that solution, when you're solving it, what will happen is all of your variables will eventually drop out. Through your processes of substitution and elimination, the variables will all drop out, but you'll end up with a solution or a statement that is always true. We'll look at that example down below here in just a moment. Then lastly, we have our no solution, and our no solution would occur when there are no points in common. So there's nothing in common. We talked about that visual image up above. That solution is said to be inconsistent. I have an extra blank here. We'll just get rid of that. I didn't mean to include that. Okay, our no solutions are said to be inconsistent, meaning you can't find anything. And also, all the variables will drop out once again. And when those variables drop out, you will end up with a statement that is never true. Now, as I mentioned just a moment ago, that our methods for solving these equations will be the same strategies that you used in your Algebra 1 courses for systems of 2 variables, and you probably would have done some of this in your Algebra 2 courses, but those strategies would be substitution and elimination. Now, sometimes one method is better to use than the other, but either method is always available. It's just sometimes certain methods will incorporate or introduce fractions, and no one really wants to have to do that. So as I mentioned up above, as you're starting to solve these problems, going through your substitution and your elimination, you will end up with a variety of types of answers as you're working. So I mentioned that you might have the scenario where all the variables drop out and you're left with just some numbers. And when you look at that resulting statement, this 3 equals 7, what we understand is that answer doesn't make any sense at all. That's certainly not possible. There's no way 3 will ever be 7. So this would be a situation where we would say that there's no solution. Okay, so that would be one way. It's also possible that they would ask you whether the system is consistent or inconsistent, and you would say it's inconsistent. Our next scenario would be where you can get 3 unique numbers for x, y, and z. You get a unique variable for answer for x, a unique value for y, and a unique value for z. You get 3 distinct values there. And when you get those 3 values, then you would just put them in alphabetical order. And that would be your solution. That would be the nice point. Think the corner of the room. The last scenario, of course, is where, again, all the variables drop out, but the statement that you end up with is always true. It could be 7 is 7, or 0 is 0, or 5 is 5, but it's something that perfectly equals itself, and that would be our situation of an infinite number of solutions, meaning an infinite number of points. Do not say all real numbers, because that's not what that means. We're describing how many points or what points they have in common. So the answer is infinite solutions. It is not all real numbers. And they also could ask you again, inconsistent or consistent, and you would say it's consistent because you can find a solution, but it is dependent because we will have an infinite number of solutions there. In the next couple videos, we're going to actually look at some examples and work some out and see what this looks like in terms of the algebra.